Hello students, I welcome you in today's session of physics, and in physics you can see here I am going to present you chapter number 26, which is your atoms. Clear? So before going to start the chapter, just have a look what we have to study in this chapter. This is your syllabus. First one, we have to talk about the alpha particle scattering experiment. After that, Rutherford model of atom, then Bohr's model, energy levels, hydrogen spectrum. Clear? So first one, you see that the alpha particles scattering experiment. This is the first topic. And what's the first topic? In 1906, Rutherford observed that when a sharp beam of alpha particle, what is the alpha particle? Is 2He4. Clear? This is your alpha particle. So in 1906, Rutherford observed that when a sharp beam of alpha particles falls upon the photographic plates in vacuum, a sharp image is obtained. Clear? So if, however, a thin foil of metal is placed in the path of the beam, the image becomes diffuse. So this is due to the scattering of alpha particles by the atom of the foil. You can see from this figure, this is the alpha scattering experiment given by Rutherford. Now in 1909, Geiger and Marsden, you can see here, made a series of measurements on the scattering of alpha particle, which led to the discovery of atomic nucleus. These Geiger and Marsden demonstrate there is a nucleus in the atom. So their experiment setup is shown in the figure. So a beam of high energy alpha particle is emitted from a radioactive element which is called as polonium, was made to fall on a very thin gold foil. So the whole arrangement was kept in vacuum so that there were no collision of alpha particle with the air molecules. Clear? So the particle while passing through the gold foil were deflected, that is scattered through a wide range of angles. Here you can see the particles are deflecting over a wide range of angles. So the particle is scattered in various directions were counted by a scintillation counter. So it was found that although most of the particles scattered through angles of the order of 1 or less, but a smaller number, say about 1 in every 10,000, is scattered through 90 degree or even 180 degree. So this large angle scattering of alpha particle could not be explained from the prevalent ideas about atom. Now in 1911, Rutherford explains successfully the large angle scattering by proposing a structures of the atom in the following ways. You can see here this is the Rutherford experiment, and the above one is the Geiger Marsden experiment, the experiment number 1. This is the Geiger Marsden and this is your Rutherford experiment. So you can see from this figure, most of the alpha particle passed almost straight through the gold foil without being affected in any way. From this, Rutherford concluded that atom is almost hollow inside. In no case it can be solid, was assumed by Thomson. Now come to the second one. Some of the alpha particles were deflected at small angles and their angular distribution was indefinite. Now since alpha particles are positively charged, the part of the atom deflecting them must also be positive. So on this basis, Rutherford concluded that the whole of the positive charge of the atom must be concentrated in a very small space. So it cannot be distributed uniformly inside the atom as is what assumed by Thomson. Now come to the third one. Very few of the alpha particles you can see here from this figure are scattered at an angle greater than 90 degree from their initial path and return back. From this, it is evident that when the high speed positively charged alpha particle pass through the atoms of the gold foil, then a few of them experience such a strong repulsive force. Clear? So as to return back. So on this basis, Rutherford assumed that the positive charge in the atom is concentrated in extremely small space which is at the center of the atom, and this space is called the nucleus. Fine. So from this experiment he described that the nucleus is positively charged. Now calculation shows that the radius of the nucleus is of the order of 10 to the power minus 14 meter, while the radius of the atom is of the order of 10 to the power minus 10 meter. Fine. The radius of the nucleus is only a 10,000th part of the radius of the atom. So in the rest of the empty space of the atom around the nucleus, there are electrons only. So an alpha particle which happens to approach the nucleus very closely experiences a very strong repulsive force and is deflected by a large angle. So if, however, the nucleus is very much smaller in size compared to the atom, then the probability of alpha particle reaching close to the nucleus will be very small. So the number of alpha particles scattered at large angle will also be very small. So experiment confirm this fact, it has been seen that only 1 out of 20,000 alpha particle is scattered at an angle greater than 90 degree. Thus, this experiment gave an important information regarding the extension of the positive charge in the atom. I hope you understood. Now come to the fourth one. So another important information obtained from the alpha particle scattering experiment was regarding the scope of the Coulomb's law. What is the Coulomb's law? I told you E is equals to 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now Rutherford assumed that when an alpha particle passed through the atoms of the gold foil, the repulsive force exerted on it by the nucleus, because the alpha particles is also positive in nature and the nucleus is also a positive charge. So the particles which on passing through the atoms remains quite far from the nucleus, nucleus experiences a small repulsive force and it goes through without any appreciable deflections. Fine. But the particle which is passing close to the nucleus experiences a large repulsive force and is scattered through a large angle. So Rutherford, on the basis of Coulomb's law, calculated that the number of alpha particles is scattered at different angles and found that the scattering of the alpha particle by the nucleus is in accordance with the Coulomb's law. So in other words, Coulomb's law holds for atomic distances also. Now come to the fifth one. Rutherford also acquired knowledge about the positive charge in the nuclei of the atom of different metals. He made alpha particles to fall on the foils of different metals as gold, silver, platinum, etc. and counted the number of particles scattered in a definite direction and found that this number was different for different metals. From this he concluded that the magnitude of the positive charge in the nuclei of different metals is different. So greater the positive charge in the nucleus, greater will be the repulsive force on the alpha particle and larger will be the angle by the alpha particle scattered from its path. So Rutherford shows analytically that the number of alpha particles scattered with a definite range of angle by metal foil is directly proportional to the square of the magnitude of the positive charge in the nucleus and of the metal. So on this basis, Chadwick, you know very well the name Chadwick, determined the positive charge in the nuclei of different metal and found that the positive charge in the nucleus of the metal is how much, which is your Ze, where Z is the atomic number and E is the charge. So charge on the electron, Z is a constant for the metal, Z is called the atomic number. I hope you understood. Now you can see here the distance of the closest approach estimation of the size of the nucleus. What is the size of the nucleus? You can see here from this figure. So we can estimate the size of the nucleus by the scattering of alpha particle. The alpha particle are emitted with a kinetic energy from the radioactive sources. The particle which grows straight head on towards the nucleus reaches closest to the nucleus. So as the alpha particle approaches the nucleus, the electrostatic repulsive force due to the nucleus increases and the kinetic energy of the particles goes on converting into the electrostatic potential energy. So when whole of the kinetic energy is converted into the electrostatic potential energy, the alpha particle can go more towards the nucleus and returns back its own path. So the alpha particle is scattered through an angle of 180 degree. You can see this figure. The positive charge on the nucleus is how much? I already told you is Ze. So on the alpha particle is 2e because the charge over is 2He4. So if RO be the distance of the closest approach of the alpha particle to the nucleus, so at this instant the potential energy of the alpha particle is how much? Is equals to, you can see this is the potential energy and this energy comes from the Coulomb's law, which is 1 upon 4 pi epsilon naught Q1 Q2 by R square. So finally it's out to be 1 upon 4 pi epsilon naught 2 times of Ze square by R naught. Fine. So if the initial kinetic energy of the alpha particle be K, so then at the instant of the closest approach U is equals to K, that is K is equals to 1 upon 4 pi epsilon naught 2 Ze square by R naught, or you can write here this is the R naught 1 upon 4 pi epsilon naught 2 Ze square by K. So this is the expression for the distance of the closest approach R naught of the alpha particle to the nucleus. So clearly for a given nucleus the value of R naught depend upon the initial kinetic energy of the alpha particles. Fine. So if on the scattering experiment the velocity of alpha particle of mass 6.27 into 10 to the power minus 27 kg moving toward the gold nucleus was this much, the kinetic energy of the particle is, you can easily find out, 1.48 into 10 to the power minus 12 joule. Now put the value in this formula of Ze and all the expressions. So finally the radius comes out to be 2.5 into 10 to the power minus 14 meter. So we can say that an alpha particle having the above energy can approach the nucleus closest to the distance how much? 2.5 into 10 to the minus 14 meter. Clear? Now come to here. So clearly, particle with kinetic energy greater than a certain limit cannot be scattered back to the nucleus. Fine. Now we will discuss about the Rutherford model of atom. You can see here, this is the third one, and this is the Rutherford model. So on the basis of the observation of alpha particle scattering experiment, Rutherford presented a model of atom called the Rutherford atomic model. And what happened in this model? In this model, the mass of the atom leaving the mass of its electron and its whole positive charge are concentrated at its center. Clear? Of the atom in the nucleus is of the radius, I already told you, 10 to the power minus 15 meter. Around the nucleus are distributed the electron in hollow sphere of the radius is how much? 10 to the power minus 10 meter. So the total negative charge of the electron is equal to the total positive charge of the nucleus. The atom as a whole being electrically neutral. So the Rutherford assumed that the electron in the atom are not stationary. As they were so, they would be pulled into the nucleus due to the strong electrostatic force of attraction which is imposes by the nucleus over the electrons. You can see here electrons are moving around the nucleus and nucleus is positively charged, but are revolving around the nucleus in different orbits, and the necessary centripetal force is provided by which electrostatic force of attraction between the electrons and the nucleus. So Rutherford atomic model was supported by the periodic table of element. Now here you can see there are few drawbacks of the Rutherford model. So the first one regarding the stability of atom. Rutherford not able to justify the stability of the atom, and the second one is regarding the explanation of the line spectrum. So the detail you can read it by yourself. I am just taking about the brief. Fine. So these are the 2 points which are the drawbacks of Rutherford atomic model. Now come to the concept of atomic number, mass number, and the neutron number, the fourth one. Here, this thing we are going to discuss. So now we know that the mass of an atom is concentrated in the nucleus. So the entire positive charge in the nucleus, we shall learn that the nucleus has proton and neutron. The nuclear particle, which is a proton and neutron, are also called nucleons. Clear? The proton give positive charge to the nucleus, while the proton and neutrons together give its mass. Fine. So the total number of proton and neutron is equal to the integral value of atomic mass and is called as the atomic mass number. Fine. So the number of proton is called the atomic number. The place of element in the periodic table is decided by its atomic number only, not by its mass number. This thing you should keep in mind. Now since the atom has the same number of electron in the nucleus of proton, hence the atom on it, so the whole is electrically neutral. This is the condition why the atom is electrically neutral. So the charge on the electrons and the mass of hydrogen are exactly equal to those of a proton. So there are only one proton in hydrogen nucleus. So the atomic number of hydrogen, you know very well, is how much? 1, and its mass number is also 1. So the deuterium heavy hydrogen nucleus called deuteron has a positive charge plus E, but its mass is nearly 2 times of the mass of proton. Hence it has 1 proton and 1 neutron. So the atomic number of deuterium is 1 and its mass number is 2. The helium nucleus has a charge plus 2e, but its mass is nearly 4 times the mass of proton. So helium nucleus has 2 proton and 2 neutrons. Clear? Thus the atomic number of helium is 2 and its mass number is 4. The lithium nucleus has a charge of plus 3, but its mass is nearly 7 times the mass of proton. Hence its nucleus has 3 proton and 4 neutrons. That the atomic number of lithium is 3 and its mass number is 7. So there are the different elements is given here and respective their mass number. So you can write it, atom is written as Zx to the power A, the mass is A minus Z, is called the neutron number. Clear? Now we will discuss about the Bohr's model of atom. What is the Bohr's model? This is the important one. So in 1913, Professor Niels Bohr removed the difficulties. I told you the drawbacks of the Rutherford. Rutherford not able to explain the stability of the atom. So to overcome these drawbacks, a new scientist, which is Niels Bohr, gave his ideas. So to remove the difficulties of the Rutherford atomic model by the application of Planck quantum theory, for this he proposed the following 3 postulates. Now what are the postulates? Let's discuss. Electron can revolve only in those orbits in which their angular momentum is an integral multiple of h upon 2 pi, where h is the Planck's universal constant, and if the mass of the electron be m is revolving with a velocity v in an orbit of radius r, then its angular momentum will be mvr. You know very well p equals to mv, so we can write here p mvr. So according to the Bohr postulates, you can write it mvr equals to nh upon 2 pi. where n is an integer of 1, 2, 3 and is called as the principal quantum number of the orbit. So this equation is called the Bohr's quantization condition. Now come to the second one. While revolving in stable orbits, the electrons do not radiate energy in spite of their acceleration towards the center of the orbit. Hence, the atom remains stable at its existence stationary state. Now, see the third one. When the atom receives from outside, one or more of its outer electron leave its orbits and goes to some higher orbits. Clear? This is due to the excitation. So, this state of the atom is called the excited state. Fine. Here you can see from the figure. So the electron in the higher orbit is remain stay at the how much time, 10 to the power minus 8 second, and return back to a lower orbit. So while returning back, the electron radiate energy in the form of electromagnetic waves. You can see from this figure, this one. So if the energy of electron in the higher orbit is how much, E2, then in the lower orbit is E1, then the frequency nu radiated by the wave is given by h nu equals to E2 minus E1, or you can write nu equals to E2 minus E1 by h. So this equation is called the Bohr frequency condition. I hope you understood. Now here you can see this thing we have to discuss, and we will discuss this in our new next lecture. Till that, students, do study. Thank you, class. Thank you very much.